Completed in 1993, Yokohama Landmark Tower was Japan's tallest building and remains the third tallest today. Among the many challenges in designing a superstructure, lateral forces caused by wind and seismic activity are the most critical considerations. For the Landmark Tower, the results of structural simulation told a clear story. Wind forces dominated, surpassing seismic loads throughout much of the tower vertical span. In a country known for earthquakes, it was the wind that proved to be the greater challenge. The overturning moment and lateral shear forces at the top of the tower were predominantly driven by wind. Today, we will look at the outline and control techniques of structures created to control lateral forces. First, four-corner structure. To resist force of the wind, a distinctive solution was formed for massive, inclined mega columns, each leaning outward from the tower's corner with deliberate intent. The most striking feature of these four columns lies in their precision. As they rise, each one inclines inward, leaning softly toward the building's core. The tapered form streamlines airflow and reduces lateral wind pressure. The increased structural stiffness reduced the tower's natural period of vibration to approximately 6 seconds. These prevent dangerous resonance with strong winds at certain frequencies. The beer vendor frame collects vertical loads, including floor slabs and exterior walls, and transfers them to the inclined corner columns. Wind pressure on the facade is observed by the beer vendor frame, dispersed within it, and transferred to the inclined corner columns for overall wind resistance. The inclined columns and beer vendor frames form an integrated external tube structure, the core of the Landmark Tower's lateral load resisting system. The four lower corner columns bear extreme vertical and wind-induced load. Conventional steel required oversized column sections to handle the stress, limiting architectural design and cost efficiency. SM570Q high-strength steel was used, offering a yield strength over 430 MPa, allowing smaller sections to resist greater forces. SM570Q is not only strong, but also designed as a vertically restrained steel. In the lower structure, the CFT method was used, filling steel tubes with high-strength concrete. The steel tube confines the concrete, enhancing its compressive strength and ductility, while the concrete prevents local buckling of the tube on the road. Up to 16 internal diaphragms were installed inside each CFT column to increase toughness. Due to the diaphragms, the concrete had to pass through 180 mm openings. Filling such narrow and complex spaces with ordinary concrete was nearly impossible. This led to the use of ultra-flowable concrete, known as fire concrete, with a slump flow over 65 cm. It fills narrow spaces without vibration, maintaining level flow on its own. It was placed using a press-in method through injection pores at the base of the columns. This method enabled void-free filling up to 40 meters. For the main exterior columns, 25 meters were filled by injection and 15 meters from the top. To resist lateral forces, the Yokohama Landmark Tower adopted an efficient dual-tube structural system. The first axis of the dual-tube system is the inner core tube, located at the building's center. The core tube acts as a strong structural unit, resisting lateral forces and torsion from wind and earthquakes. Surrounding the core, the external tube forms a second layer of defense against lateral forces. When wind strikes, windward columns experience tension and leeward columns compression, resisting the building's bending. The side frames resist shear force and maintain the tube's shape. In a moment-resisting frame, the concrete floor slab acts as a rigid diaphragm in a horizontal direction. The diaphragm transfers lateral forces to both the inner and outer tubes, finding them to act as a single structural unit. Connected through the flow slabs, the inner and outer tubes share lateral loads in proportion to their stiffness. The external tube carries about 60% of the total lateral load, with a higher share in the lower CFT sections. A system of strong steel braces is concentrated in the upper floors, between levels 42 and 67. These large axial V-shaped braces directly and rigidly connect the core tube to the outer corner columns on all four sides. When the building bends under wind, deformation of the core is immediately transferred to the outer columns through the braces, which experience tension on one side and compression on the other. The braces help the core carry an additional 20 to 30% of the building's total lateral shear force. This prevents excessive force concentration in specific members and enhances the efficiency of the lateral load resisting system. Finally, tuned active damper core TAD. Structural design ensures the safety of the landmark tower, but at high elevation, micro vibrations become a concern. To address these subtle vibrations, a TAD tuned active damper system was installed at two locations on the top floor to detect and reduce building sway. This is tuned active damper. Each unit contains a control mass weighing 680 tons, about 0.6% of the building's total weight. Driven by powerful AC servo motors, the 680-ton mass moves up to 1.7 meters horizontally, with a maximum output of 180 kilowatt and control force of 15 tons to counter building vibrations. The T in TAD stands for tuned, meaning the damper is precisely calibrated to match the building's natural vibration period. The landmark tower's TAD uses a multi-stage pendulum, tuned to the building's natural period of about 5.4 seconds, allowing the mass to move in a position and effectively cancel out vibration. The A in TAD stands for active, meaning the system autonomously assesses the building's condition and responds accordingly. High-performance AC servo motors and precision burst screw systems move the 170-ton mass quickly and accurately in the calculated direction and speed. Simulation and scale model tests show that at a wind speed of 43 meters per second, a once in 5 years event, the TAD reduced peak acceleration at the top floor from 34 gallons to 14.3 gallons, a 58% reduction. In case of malfunction, the system switches to a passive tuned mass damper mode to maintain damping performance, and emergency brakes activate if excessive motion is detected. Inclined columns resist overturning. SM570Q steel and CFT withstand high compressive loads. The dual tube structure and braces resist lateral and torsional forces. The TAD system controls micro vibrations. These technologies enable the Yokohama Landmark Tower. Next week, we will focus on earthquake load.